Today we talk about concentration. So we have here as an example the parabolic concentrator. So you have the effective area from the sun coming in. In general, a parabolic concentrator can only concentrate direct solar irradiance, cannot make use of diffuse irradiance. So we have the effective area. The irradiance is then reflected on the focus area here. Here the absorber area could be a point or could be an area. According to that, here you see we have the concentration radio. There's some simulation software, for example, company. For some time, it was even the most famous thermal simulation program for solar thermal systems. Here's some description. So it's just described how this works. There's a front end where you can enter your components, the collector and the storage system and so on. And then the different pipes and so on, additional components, additional heating. And then you have a description of the array. For example, here 6 collectors with 1 square meters each. Then you have a tank here with 300 liters, for example, the height and so on. So it also calculates the stratification inside the tank and the losses if its stratification not perfect. And it carries out a simulation between 1 and 6 minutes. So it's just based on hourly climate data. Better if you have half an hour, minute data. And then it calculates the mass flows within every component and perform a step within 1 to 6 minutes. Yes, we have the tank layers, so the stratification inside the tank is also calculated. So you can start a simulation now. And so you see here represented by the different colors, and you see here on the lower left part, you see the time. So it's 5 o'clock in the morning. Now sun goes up at 7, 8 o'clock. It's heating up. It's getting orange. So you have about 40, 50 degrees. 10 o'clock now, you have already 60 degrees. Also, the tank is getting heated up. So the tank is not stratified anymore. It's almost equal temperature. And now we have in the afternoon, it's now 16 o'clock, 4 p.m. And then sun is setting, and then you take out water here, and from the lower part, cold water is entering, and you take up of the hot water. Then hopefully it's night. In the morning, then the hot water has been enough to supply hot water for the whole day. Now it's simulated a cold day without a lot of irradiance, and you see that the hot water reservoir is drastically decreasing. Then you have a nice presentation sheet for the results for the investor to see what components are you using and how much it costs, how much is the return, what part of the energy you can get, and how much carbon dioxide emissions are saved. Here you see the solar contribution during the year. So the yellow part is a solar contribution. So you see here in the summer months, it's almost 100% contribution by solar. In winter, it's less. Then you can do also energy balance schematic. So you can take a look at the input and output of the different components. First starting with irradiance, how much irradiance is there. So that's 6.9 megawatt hours is coming in. And so you see all the different losses and the internal piping losses and the tank losses and the final energy and so on. You can compare different principles and different components to each other. So here you can have a 1 tank compared to a 2 tank solution. You have a database which is updated with all the data from new companies which develop new kinds of collectors, not inverters, so sorry. Here you see, for example, a base with the Wagner collectors and the different sizes they have and so on, and the different properties. You can also use air collector systems. It's also possible, but the thermal capacity of air is very low, so you have to have a high throughput of the media, means air, so it's not as efficient as liquid collectors. But it's possible if you have the opportunity. It calculates the profitability of such a system. But it's all the things that they have collected data from all over the world, starting with irradiance, but also from the different components available in different countries. Here you have additional heating. Sure, in Germany, for example, you need some additional heating. Then you have the integration of different sources for irradiance here. So you can select on a world map the location here and have a daily and a yearly or seasonal change of irradiance and so on. So there is some calculation on it. Some music here also, whatever. So it shows again just this comprehensive profitability calculation, separate output of solar fraction. So you can compare different kinds of systems here as an example here. You see different locations and the global irradiance at each day, for example, here. Here, this is the final result. So you see the hot water contribution was 62%. I think the new version also has a nice photographic layout, so you can show to the housewives and so on, which usually don't like the collectors because it looks ugly, but you can discuss whether it's nice looking or not. So here you have another solution, so it's 50% only. And so you can here calculate the investment and the return of investment. And after here, for example, this example, it makes only profit after 16 years. It's poor, but usually should get a quicker return of investment. You can also put it large scale. So here's an example from a solar energy generating system in the desert of Arizona. So you have a solar truck system with a focus line. It's attached to storage there, so it can also run through nighttime. Usually don't use water there, not because of it's freezing. You use oil because you can heat up temperature up to 300 degrees Celsius without producing steam. You produce the steam then with a heat exchanger, and the high pressure steam goes here inside the turbine, powers a generator, and you power some houses. Then you liquefy by condensing the steam here. Should be the pipe is going through here through the pipes because it was originally German and I put the English expression over it. Then you go via pump, and this increases the pressure. It consumes quite a lot of energy because you have to create a high pressure here. And then additionally pressure is created by the steam generator here. You can also put an additional heater there, even in the desert. Sometimes there are clouds and so on. And then the storage is empty. You can have additional natural gas power heating then. In this case, at the ZEC systems, they even have a two-stage turbine, so they are not used going directly to the cooling tower. They use a second stage of the turbine in order to increase the turbine efficiency. Main thing is you have two cycles, so the solar cycles with a oil here and the water steam cycles here. An additional thing to mention here is the convective air steam power plant. So you have here quite large area covered with glass or transparent plastics, and then the ground heats up and the air is getting lighter and it flows through a chimney, which can be quite large, could be some 100 meters high, and then it's powering a turbine. This flow. There's been some experimental setups in southern Spain with 100 kilowatt. But there was original planning of a 1 gigawatt power plant in the Australian desert with 1 kilometer of chimney, but it never been realized because meanwhile photovoltaic got so cheap and the constructive cost is quite high. So it's a bit stalled here. Actually quite good idea, but due to the high constructive necessities, it's not developed further anymore. So we have here the idea with the so-called Desertec Project in 2009. The basic idea was to generate electricity in North Africa by wind and solar, both with solar thermal systems, which cost 4 to 5 cents a kilowatt hours now, And due to the attached storage, you can have 8,000 full load hours per year. That means it's running through all the year. Or photovoltaics, which battery storage quite expensive, so it was just considered it works during daytime. And there you can achieve 2,000 to 2,500 full load hours. At this time, cost was estimated to 4 to 5 cents per kilowatt hour. But this is a cost you can achieve with photovoltaics now, even in Germany with low irradiance levels. And for high irradiance desert, you are in the vicinity 1 to 2 cents per kilowatt hour. So it got a bit stuck, the project. Anyway, it's quite a good idea. But at the moment, Morocco is built such a big system with 500 megawatt, but it uses basically the energy of its own on its own. So we didn't hear anything further on it. You have to consider also the transmission costs, which is quite optimistic here for 1 cent per kilowatt hour. Also goes here through Libya and Algeria. And so the investors were afraid of investing there because they don't know whether the investment is safe and so on. And therefore, this got a bit stuck, this project. We have an exercise for that lecture. So first question is, which are the loss mechanisms at solar thermal energy systems? What is the advantage of solar thermal electric power systems in terms of possible storage compared to direct solar electricity conversion via photovoltaics? What are the two main technical disadvantages of concentrating power systems? What could be an advantage? If you take a look at the collectors from the page 70 to 73, Bayer has the option for two collectors. One with a selective coating, it's a bit more expensive. It costs 120 euros per square meter. Another with a non-selective absorber costs only 100 euro per square meter. He wants to know whether it makes sense to spend more money on the selective absorber when the required temperature difference is 50 Kelvin. Or the second part of the question is if it would be 75 Kelvin. Then another part of the exercise is what would be the generation costs in cents per kilowatt hour for solar thermal energy over lifetime, let's say 20 years. In Portugal, south of Portugal is Faro. There we have a global annual irradiance of 2,000 kilowatt hours per square meter per year. Then we would consider a thermosiphon system, which consists of a flat plate collector with single glass cover and an effective area of 2 square meters. And this would cost there around 1,000 euros, including mounting. In Paderborn, we cannot apply a thermosiphon system, so we have to use a pumped system. And also the area has to be bigger, so we have considered a 4 square meter collector. This is considerably more expensive. It costs about 5,000 euros. To compare both cases, and in both cases, the storage tank of the system is considered to be sufficient to accumulate and distribute all collected irradiance. So I made it a bit easier for you. You don't have to consider the storage size. So the question is, what has to be considered first besides the accumulated irradiance for an operation Paderborn when we calculate, we can consider a global irradiance during the year of 950 kilowatt hours on a square meter during a whole year. To select the adequate characteristics, so you choose the graph in page 73 that is closest to the average irradiance value for the whole year during daytime. Then we have to consider also the time it needs to heat up such a thermal collector. Here we consider a size of 2.3 square meters. For example, the system we saw on page 74, the Turkish system, and to heat up the water inside the attached storage tank, which is also described there with a volume of 160 liters and incoming temperature of 20 degrees, which is typical for tap water in the tropics, and you want to heat it up to 60 degrees Celsius. The temperature of the tap water should be considered to be equal to ambient temperature, and the temperature inside the collector is equal to the temperature inside the storage tank. So first we consider a constant irradiance value of 800 watt per square meter, then we consider 400 watt per square meter, and last but not least we consider a 200 watt per square meter only. Then we consider the irradiance efficiency graphs at page 73. The specific heat capacity of the water you need that for the calculation is 4.18 joule per gram Kelvin, and the water density is 1 million grams per cubic meter or 1000 kilograms per cubic meter. The next question is how you can eventually get a different water temperature from a single storage tank. I explained it already several times. And what prerequisites are necessary. What else can you do if you need a lower water temperature than the water temperature inside the storage tank, for example 30 instead of 60 degrees. The solutions are here, which are the loss mechanisms at solar thermal energy systems. So the optical losses at a typical flat plate collectors are, so we had reflection on the glass surface. We have absorption in the covering glass. Remember the graph here, we saw that reflection, both interfaces together are 8%. And we have reflection of irradiance leaving the cover glass. Also, this is both 4%. So we have reflection on the glass surface 4%, absorption 2%, and the reflection of irradiance on the interface from the glass to the air again 4%. Reflections at the absorber, I think it was 6% or so. Then we have the thermal losses. This is the heat conduction from absorber to the frame or the ground or the roof. Then we have convection, the natural convection. The warm air is lighter than the cold air and it's lifted off from warm surfaces and is substituted then by flowing cold air. And thermal radiation, so there is a radiation exchange between the warm surfaces, between the ground, especially between the sky. Here you see it again, so just as I mentioned here 8% means that both losses is 4% here and 4% here, absorption 2%, reflection at the absorber it's not 6%, 8%, it depends on the quality of the manufacturer and so on. Here the thermal radiation and the thermal conduction, and here 13% for the natural convection. The question was, what is the advantage of solar thermal electrical power system in terms of possible storage compared to direct solar electricity conversions via photovoltaics? So we have here a solar thermal energy can be easily stored in a thermal storage, for example in a water tank or phase change material. Costs are about 5 cents per kilowatt hour of storage. So sometimes they are more expensive, or often they are more expensive than the actual generation of solar thermal energy. Electrical storage is much more difficult and more expensive. For small scale storage is in the vicinity of 15 cents per kilowatt hour for small scale storage. If you go to large scale storage, for example pump hydropower plant, prices may go down to 5 cents per kilowatt hour. Next question was, what are the two main technical disadvantages of concentrating power system? What could be an advantage? This was that you can only use the direct part of solar irradiance. That is weather and site dependent. The reflectors or the lenses have to be tracked according to the position of the sun. Plus you have to also keep the mirrors and the lenses clean because they are very sensible to that. Advantages is that the higher temperatures can be achieved that allow some applications, and the so-called Carnot efficiency, which is highly dependent on the temperature difference. And you have a high temperature difference, then you have a high conversion efficiency. So this is a Carnot efficiency, if you know from thermodynamics, or if you listen to my lecture on Energietechnik, we discussed also a lot about it. So it's 1 minus T ambient divided by T collector, or not T ambient, or the T output of the system. So now we do some calculations about investment. So we have the selective collector with 120 euros per square meter and a non-selective absorber at 100 euros per square meter. And the two temperatures, 50 Kelvin and 75 Kelvin of not temperature but temperature difference. And we take a look at the curves again. So we have here the different types of solar collectors, and here you see the A vacuum collector, sure, it stays at high temperature for a long time, it had optical losses, and also the constructive means are more excessive. And what we compare here is the middle blue and the middle blue and the dark blue line here. So we take a look here. So we have here temperature difference of 50 Kelvin for the dark blue, so non-selective absorber. We have a conversion efficiency of 40%. And if we go up here for the same temperature difference, but to the collector with a selective absorber, we have a conversion efficiency of 54%. So advantage. And for the 75 degrees of temperature difference, we have about 11% of conversion efficiency for the non-selective absorber, and for the selective absorber we have here 39% of conversion efficiency. So let us see whether it pays off. So we took from the graph here the conversion efficiency at 50 degrees. We saw a 40% of conversion efficiency for the non-selective absorber and 54% at the selective absorber. At 75 Kelvin temperature difference, we see exactly the number is 11.5%, while the conversion efficiency with the selective absorber is significantly higher, speaking at 39%. So we take a look. So from the graph, we can read that the relative cost is the cost per square meter and the conversion efficiency. So we have here about 250 euro for an ideal collector that would convert everything into thermal energy, while it's for the selective absorber, the area required it's less, and also the costs are less, 222 euro per square meter. At 75 Kelvin temperature difference, we have then 870 euro per square meter. And while we have at the selective absorber, we have 307 euro per square meter only. So I just took for granted the cost of generated energy is proportional to the purchase price of the collector, reversibly proportional to the conversion efficiency. So we come to the next part of the exercise. The question was about the generation costs in Seville, Spain. We didn't take Faro, but it's about the same irradiance value. So we have here the yearly irradiance is in Seville 1,944 kilowatt hours per square meter per year. If we take it for 365 days and 12 hours, so we have an average, so we take only from the morning to the evening, we not take 24 hours, we take just the daylight hours, and it's about 400 watt per square meter, and then we choose a graph with the 400 watt per square meter. That means we would have an efficiency of 37%, and then Paderborn irradiance is only half of that, speaking 950 kilowatt hours per square meter per year for the days, and for the 365 days during daytime. This is equivalent to 216.9 watt per square meter. So therefore we choose the 200 watt per square meter graph, and for the required temperature difference doesn't reach that value, so we can not use that. So we have to use a different technical solutions, for example a vacuum collector. So here temperature difference here at 200 watt per square meter, and then we have the conversion efficiency here at 37%, and we have the generation over 20 years. That means we have this irradiance value for the whole year times 2 square meter times the average conversion efficiency multiplied by 20 years. So we have about generation of 28.77 megawatt hours. In general, the calculation is very rough. If you want to do really very precise calculation, you should use simulation programs just as TSOL. Then the specific costs are, so we have the investment costs, which is about 1,000 euros, and generated heat during those 20 years. So we have a generation cost of about 3.848 cents per kilowatt hour of thermal energy. So the specific costs are already higher than PV electricity. If you consider the last tenders of the electricity companies in Portugal, there have been offers about 1.5 cents per kilowatt hour of electrical power. You have also the costly installation, the hot heat pipes. So this is, therefore, I'm very brief now with the solar thermal systems. I would spend more time on PV electricity. So we take a look at the warming up, so more in the dynamic part. We take a look at the area of 2.3 square meters and a volume of 160 liters. And we heat it up from tap water from 20 degrees to 60 degrees. Here we take into consideration a constant irradiance of 800 watt per square meter, which is quite idealistic. They never have a constant irradiance, but we saw if we come very close to the Seville location of 400 watt per square meter. 200 watt is just like Paderborn's average irradiance. We see here the heat required and the heat provided by solar. You have to just match this. So the required heat has to be covered by solar. We calculate it now. So this time required to achieve that is here the temperature difference multiplied by the heat capacity of the water times the volume times the density of the water rho and the irradiance value E and the area and the conversion efficiency at a certain irradiance value. And if you put in the numbers, so we have here chapter 261, we have a temperature difference of 40 Kelvin and thermal capacity of 4.18 joule, can also translate in watt seconds per gram Kelvin. We have the water density and the tank size. Yes, it's 160 liters. That is equal to 0.16 cubic meter. And the first part, we have the irradiance value of 800 watt per square meter. And the conversion efficiency is quite high, as 63%, if you take it out from the graph. So it would, to complete the complete tank, it would require about 6.41 hours. So this efficiency was taken from page 70. For the next stage, if you only would have an irradiance of 400 watt per square meter, it's basically the same calculation. We just have the lower irradiance plus lower efficiency. We have to consider the lower efficiency also. So it's not only double the time, it's almost 3 times the time we need to heat it up, 18.78 hours. If we go to the very low irradiance, just like the average irradiance in Paderborn, it would even require more than 400 hours to heat it up. How you can get eventually different water temperatures. So I was talking about a lot of time, so you can do it by stratification inside the tank. So if there's a little water movement only in the tank, the hot water stays on the top and it can be extracted from the top, while you can fill up cold water on the lower tank part of the tank. Usually as a prerequisite, you have to have a tank with preferably a large vertical extension and a little water movement. Usually they are mounted horizontally, which is not the best thermodynamically, but due to space limitations. The cooling can be achieved by operating the solar system as nighttime, so we can provide cooling by thermal radiation exchange with the sky or by water evaporation. That's it. Thanks a lot, and we see us next week.